We are AstronEra and we have been doing these astro streams since past 3 months now, and it's been going really great. Everybody's been enjoying these live streams, and they want us to do more and more. So we keep finding more and more interesting people like Oz here to come and join with us and talk about interesting topics about astronomy, whichever topic that they would like to talk about. So we had Ellen Glad before, who spoke about the observational astronomy and their implications in the scientific work. And then we had Dr. Reut Abramovich from Israel, and she spoke about astrobiology. And we just ended with her sessions last Sunday, and those who attended, they'll be getting some quiz to fill it out so that we understand that they actually attended all the sessions. And once they fill out the quiz, we are going to send them the certificate for that. And today we have Oz from Turkey, and he's going to talk about discovering the high energy universe. So all the interesting topics like black holes and supernovae and neutron stars and stuff like that, it's all going to be there, and obviously it's really interesting, and we all are looking forward to that.
So, welcome everyone. Firstly, I want to thank AstronEra for this wonderful opportunity. It's really nice to have this beautiful scene to talk with lots of different people from different countries. It's also really nice to see relatable people like Shweta or Nimish once again. We were friends with Shweta, and I was aware of the AstronEra and the beautiful things that they are doing for years. I guess it was 5 years ago, and we had like this conversation with Shweta. And right now, seeing that this whole beautiful thing is growing up is really beautiful. And I'm really glad in the future. I really think that in the future things will become even more beautiful for AstronEra as well. For those who don't know me, who don't know me, my name is Özgür Özüdoğru. You can call me Oz, like the Wizard of Oz, because I know it's a little difficult to pronunciate my name for those who are not native to Turkey. I am from Turkey. I spent my many years in Istanbul, and right now I'm there as well. If there wasn't any sun over there, you will see the Bosphorus Bridge as well. I studied physics in Middle East Technical University in Ankara, which is the capital of Turkey. My expertise was about astronomy, and right now I graduated last year, and right now I'm doing my master's degree in astrophysics, again in Middle East Technical University. I have a really nice advisor who is also working on these high energy astronomy topics as well. So that's why I'm a little confident with this particular part of astronomy. So that's why I wanted to give this course to you and exchange this new information, because right now this field is growing a lot, and many different scientific studies are happening. Different space telescopes are being launched, and we need new enthusiastic people to get into this field and at least know about the stuff. Actually, the name high energy is a little interesting. That usually it's used by the high energy physicists, like in CERN or other particle accelerators, those who specifically work on particles, high energy particles on our planet. But that name shouldn't really confuse you. These particles don't only exist in our laboratories. There are plenty of those particles, and they are up in the space. We are not able to observe them because our planet is keeping them so that we are alive. But in other case, we would be dead. But it was a little pity for astrophysicists to look at those things, because the only way to look at all those high energetic particles and charges was to go up to space and build a space telescope to look at there. That's why this is a really growing field. It happened only 70, 80 years ago, once we sent the first particle detectors to the space during the time of the Cold War. By the way, I forgot to talk about my society as well. I am a part of the Metro Amateur Astronomy Society. I worked there for about, I forgot, like since 2014. It's about like 6, 7 years now. And I spent really nice time there. I had really nice friendships as well. We organized lots of different events in our society. We actually visited numerous cities all across Turkey to give seminars and reach out people from teachers. And together with that, we are organizing some different opportunities for young scientists So, for example, in November, we are organizing the astrobiology conferences. Because basically every weekend there will be some expert, some academic talking about different aspects of astrobiology. And then next year in 2021, possibly in spring, there will be Diltenaryurt Astronomy Days, which is another students organizing an academic physics conference, which gives a free opportunity for physicists or students from all across the world to present their work, and at the same time have this experience of meeting with different academics from all around the world. I believe we can talk about this in the future with AstronEra people as well. It will be really nice to see many people, participants from India to these conferences as well. Let me continue to the topic. As I said, the high energy astronomy is the name is a little interesting because like you don't see low energy astronomy, right? You see radio astronomers, you see optical astronomers, but the name high energy is just kept in people's minds because back in the days when these particle detectors to detect these high energetic charges, they were very few, and the amount of people who were working on those fields were really few as well. And that was the reason that in the 1950s, in the 1960s, if you were working on X-rays, people would call you, oh, high energy astrophysicist, in order to keep the community together. And the community was really small. Right now, it's growing a lot because we are getting too much information from those areas. And right now, people are more and more educating themselves in those fields. And yes, mostly we get data or observational information about the accretion disks of the black holes or the neutron stars or the binary systems from high energy astrophysics. But it doesn't mean that we only get data from the high energy part. Well, Jocelyn Burnell discovered pulsars by looking at the radio data. So we get actually right now in this modern time of astronomy, we don't get only one particular range of areas, but we are working with the whole spectrum. Right now, we're in the age of the multi wavelength astronomy, which is the basically when you publish a study, there are a bunch of different academic groups, and one particular group working on the radio part of that source, the other group is working on the optic part, the other people are working on the X-rays and the gamma rays, and then we are collecting them. And right now, in these years, in 2020, 2019, we're experiencing a new revolution, which is the multi-messenger astronomy right now is going on. And I think it will go on like that in the future because we don't have one messenger right now. That we used to have only one messenger, which was the light itself. But right now we have cosmic showers, high energetic particles raining down to the Earth. If there is a supernova happening, our particle detectors in the polars, in the Arctics, are actually getting new data, and then we actually synchronously make observations. This was happening, and at the same time, right now we discovered the gravitational waves. We are able to detect one other aspect of general relativity, and this gave us another messenger. So right now we have different academic groups differing on different ways of observing an astronomical object. So right now this is an amazing time to be alive for an astrophysicist. Everything is improving. We are discovering the cosmos. We are discovering our new models for cosmology. We are learning about even the simplest details, the locations that are incredibly close to the black holes, and we get the image of the black hole actually. So this was the main reason why I wanted to give this course, in order to give you an idea about this modern part of astrophysics and what is going on in the field. I got some questions about the difficulty of the course. Well, you might it's a really the rightful question because usually the term high energy astronomy and these courses are usually in the master's degree physics or at the very last times of their physics undergraduate. It's the reason because of that is usually when you talk about high energy astronomy, you need to talk about the physics behind those things. Because when you talk about high energy astronomy, you talk about the ultraviolet and X-rays and gamma. So you need to talk about the processes who creates those wavelengths. And then by talking about those processes, you talk about the physics of the concepts. And in order to talk about the physics of these concepts, you need to learn some math. So this is how it goes for a general traditional way of teaching high energy astronomy. Usually academics, well, what happens is that usually they start with giving too much introduction, and then they figure out that the midterms are approaching, so they didn't even start talking about the real subject, and then they got speed up really fast. I took numerous high energy astrophysics courses, and it was always the case like that. That's why I don't want to go into the mathematics or the derivations of these topics. I believe they are really necessary. If you want to be a scientist, if you want to be an astronomer, an astrophysicist, you have to know what you are dealing about, because it's possible to use the software and then just arbitrarily fit your data with some parameter. But that make you a scientist. That just makes you a good statistics person, I guess, but doesn't make you an astronomer or an astrophysicist. In order to be a good astrophysicist, you need to learn about the physical processes behind those things, which is why this source can only be a brief introduction to this field. Don't feel that, oh yeah, now I took this course, I am a real scientist and I will do all those things. No, this course will give you literacy to when you learn about, let's say, Chandra X-ray Observatory made a tremendous discovery. So you will be able to read those articles and read what's going on at the moment. But if you want to expertise in those fields, I will provide you some materials and textbooks in the lecture, so that I will be with you during that process, and you will be able to look at the derivations and the mathematics, or maybe some exercises throughout this course. But generally, the content of the courses will be mostly verbal. Actually, once I was creating the lecture notes, like they hardly include mathematical formulas. They only are very conceptual. My main goal is to give you the conceptual idea about all those objects, all those physical processes. So in the first week, we will start with the physical introduction. We are going into the definition of the high energy astrophysics, like what is high energy astrophysics, and then what does it do. And then we will shortly talk about the light spectrum, the spectrum of light, the electromagnetic theory. And then we will start talking about the processes that trigger the creation of high energy sources, the X-rays and gamma rays, such as the process of Bremsstrahlung or the Compton scattering or the photoelectric effect. We will go about those really, really important physical concepts. I will do my best to get you into this topic, so that when someone talks about, hey, there is Bremsstrahlung going on, you will understand that what that person means. This will be the first week of the course. And then in the second week, we will go through the astrophysics of these things. We will go through the objects that mostly send their data information to the astronomers with X-rays and gamma rays. And we will go into those things, such as the accretion disks of black holes, the binary systems of neutron stars, which actually we call it X-ray binaries, which actually gives the names that, oh, this is a high energy source. And then the supernova remnants, supernovae, and all those modern events, like such as gamma ray bursts, active galactic nuclei, and the really nice event, the detection of the gravitational waves. Actually, when you might have heard about these things, two neutron stars collided. And after that collision, we get a ton of gamma rays and cosmic shower. And these were actually very high energetic charges, and we get numerous amounts of information thanks to the Fermi telescope, the gamma ray burst monitor Fermi telescope. So I will talk about these astronomical objects, but as I said, I will not go through the theory of neutron stars, the theory of black holes. Well, if you want to go to the theory of black holes, I will provide you the materials. I will show you some nice introductory information about how to get yourself familiar with the general relativity. But as I said, they will be mostly in a popular science manner. But well, they won't be popular science, because I will give you the stuff. I will show you the data or the information from academic articles. So it will be like a fusion between an undergraduate physics course and a popular science article. So this is something experimental even for me. And if that works, you can see me giving about these kind of courses in the future as well. So in the second week, we will go through the astrophysics and go through the astronomical sources that we get the high energy particles from. And then in the course, I will start going into the history of this field. So basically, there are two ways of teaching science traditionally. One way is you can either start teaching stuff chronologically. Like in that year we get classical mechanics, and then we get modern physics, and then we get quantum mechanics. You can go with the traditional way, and go with the historical way. This is one method of teaching scientific things. The other way of teaching is that as a modern scientist, you have all the information, so you are able to classify yourself. You are not bounded by the historical limitations. So there are advantages of both of these forms of teaching. Like, for example, for a quantum mechanics course, the chronological way is really useful, because it is the concept of quantum mechanics is really hard to grasp. So starting from the modern physics, starting from all those experimental periods of the 19th century, the dilemma of wave particle duality of light. So these kind of information was necessary in order to get you to going for the quantum mechanics course. But I will try the second form of teaching in this course. So I will go into the history of this thing later. I will first give you the the physical introduction, and then go through the astronomy. And once we get all these information, we will look at these historical part. We will, in the third course, we will look at how this field developed, the pioneers of this field, the X-ray analysis, the timing analysis, and the spectral analysis. People like Michiel van der Klis, or Justin Burnell and Vera Rubin. So basically people who worked with these high energy objects and high energy data, and people who introduced the high energy telescopes, the Japanese and the NASA telescopes, and the other people from the different worldwide projects. And I will talk about the modern objects as well. After we talk about this historical part, we will go through the instrumentation. I will talk about a little bit about the how these processors and the microchips in those high energetic sources work, because it's easy. It's relatively easier to grasp an optical telescope. Like you know how the Galileo built his own telescope, or you are familiar with. If you are familiar with amateur astronomy, it's you can also be familiar with how the let's say a Schmidt-Cassegrain telescope works, or how a CCD works. But capturing a high energy photon is nothing like an optical telescope. You need to come up. You needed to come up with new systems, new instruments, new type of engineering to produce a series of arrays that catch high energy photons on a particular direction, and then carry this information. You should be able to transport this device to the space, and everything was new these times. I'm talking about 1980s, 1990s, where these were the times where we start to make continuous launches back and forth to space, and build the International Space Station, introduced the Hubble Space Telescope to the space. So these were the times of progress, and during those times we get a lot of X-ray and gamma ray observatories. So I will talk about the instrumentations of these a few observatories, such as the XMM Newton is a brilliant observatory. It provides us really nice imaging, just like Chandra telescope as well, and the Fermi's gamma ray burst monitor. So these kind of things. I will show you the platforms and the websites where you can find those observations, and how to download them, the places that you can use, the materials that they use, because most of the time NASA has some nice guidelines about analysis as well. So I am planning to show you some analysis. It will be, I guess it will be step by step, but it is a long process. And by just making a spectral analysis of one source doesn't mean that you are learning too many things about this spectral analysis. So instead of teaching you the principles of the spectral analysis, which is a field of academic sciences, people spend their years to become experts on spectral analysis, I will show you the basic principles, basic tools that they use, so that you will be able to play with them yourself. This is the general idea about the analysis part of this course. So basically, this is the main idea of the analysis part of this course. I will show you the basic materials, basic softwares to install, the websites, the archival places that you can download the data. And then it is up to you to do further playing with those things. I will show you one example of a nice analysis, and you will be completely free to try it. And then for those who registered the course, we will be, I believe we will be in contact, and I will gladly help you throughout all the processes. So basically, in the fourth week, I will show you these places. I will show you which software is installed. Let me just tell you this: the most efficient way of these observational software to work, function properly, is through using a Linux-based distribution or an Apple. But Linux is much better because most of the time they function through Linux terminal. So I'm just telling this right now. This doesn't mean that you are required to install Linux for this course. You are completely free to watch how I do this, and then one day, if you are able to do these analysis, you can do in an environment you want. I hear that Windows is also introducing the analysis, the Linux terminal, the Windows terminal to its system. So you don't have to install a Linux-based system for this course. But I will be using Ubuntu and probably showing you step by step how you do a simple analysis. And then I am also planning to talk to you about a little bit of statistics about these fields. Mostly in astrophysics, in the spectral analysis, they use something called the chi-squared analysis. I will briefly mention and talk about how this chi-square analysis is being done. You will not, like by hand, you will not calculate. Luckily, we are not in the 70s or 80s, so computers and robots will do the job for us, but it is important for a scientist to know about those things, as I said. So I will see about these concepts. And then finally, in the 5th week, we will go through a software that is called XSpec as a part of the F-tools of NASA. You don't need to worry about these terms right now. And then I will show you how that software works, how to clean an observation and create a scientific spectrum that you can work with, and then how to do analysis and do model fittings for these spectrum. I will also mention about the statistics and the models, spectral models of some of these observations, which ones to use, which ones to guide. So as I said, it will be like a guide for you. It will, if you ever go into these fields, it will be like a tutorial for you, but don't expect that by just watching these videos, you will be masters of X-ray analysis or about this field. So basically overall, as a step forward, if you want to be familiar with the physics of these concepts, I will provide you some books so that you will be able to look at the derivations and the mathematical principles that these physical phenomena are established. And then I will show you some materials and websites to give you the further information, further observational data for you to install and play with. These two things are up to you after you take this course. But I will be accessible to you. For those who registered the course, we will have a Discord server, and in that Discord server, you will be able to ask me questions like a forum-based, so we can have a forum-based discussion about all the concepts that I talk about. And then probably sometime after this course as well, I will be available in my free time, and I will talk to you about all those things if you are interested in these further details as well. So overall, we will collect this. We will be finishing that 5-week course with this content, and then after we finish these 5 courses, there will be another live stream just like this. Probably maybe with another person with me, like a conversation. In that live stream, we will summarize everything that we have talked about. And then after that, we will have a live Q&A session, question and answers about these things. But it doesn't only need to be about the stuff that we learned in the lecture, but also it can be about the general modern astronomy and modern developments in the astronomy. I can show you my little expertise. I don't want to say little, but relatively little, I would say, because there are many people who are experts in those fields, professors and academics. I feel like I am in the beginning part of this road, but even being at the beginning part of this road requires a lot of knowledge. So this is the amount of knowledge that I can filter myself, just like the Richard Feynman's principle. If you understand the concept properly, you are able to tell it to the people. And this is this principle that I always try to rely on my teaching process as well. So right now I am able to understand and talk about some stuff of this field. And right now I am willing to provide you the information that I have by my expertise, years of expertise in this, some years of expertise of this subject. I believe these were the stuff that I wanted to talk about. So if you have any questions about this, please feel free to join the talk right now. Thank you very much for your
Yes.
time and listening.
That'll be perfect. I have some questions for you as your own introduction. I mean, of course, I'm so excited to go through the whole course and learn about high energy universe. But I think me and everybody else over here would also like to know you a little bit as an astrophysicist, a young astrophysicist, you know. So I'd like to ask you questions in that sort of manner. Could you tell me how you got interested into astronomy?
Well, firstly, I'm flattered. Like, it's the first time somebody called me a young astrophysicist, and I really like that definition of my life. So that's why I thank you for this title. I feel really happy for. It goes back into my childhood. I know it's a little cliche, but basically, I spent my childhood in a remote area in Turkey, next to the Aegean coast, where I was spending time with my grandparents. And that place, even though right now it's full of beach clubs, but back in the days it wasn't like that. Back in my time, it was only a small village, and we were able to see the Milky Way galaxy and all those beautiful deep sky objects just by your naked eye. That kept me really close into amateur astronomy, and I started learning about these principles. I got myself like these things, the sky map, and
Mm.
like there wasn't anything like stellarium or like a smartphone, so I was just able to I need to like get the angles and the things all by my hand. So that kept me a little bit expert about these things. And then as time passes by, I started the primary school and middle school with this obsession of sky and astronomy. Back in that time, I was really fascinated with the discoveries of exoplanets. I was really
Mm-hmm.
excited when once people learned about these habitable exoplanets and the Kepler. I remember waiting for the Kepler project to like start properly, and then once it started, it's just like created an explosion of exoplanet data being accessible, and every day in different habitable planets are being discovered. And then we started to get more information about the dark matter, especially throughout the X-rays. I think after this dispute, I remember while I was in high school reading about an article written by Esra Bülbül, who was a graduate of Middle East Technical University. She is right now, she did his PhD in Harvard University, and right now doing a I think she's a researcher. She's an astrophysicist in Max Planck Institute in, and she published an article claiming that an hypothetical particle called the sterile neutrinos got some X-ray data next to the region of the galaxies where there are lots of dark matter going on. So boom, that was a lot of turn from my hand. I needed to learn all of those things. I was really into these public books, popular science books, especially the books with Stephen Hawking's book, The Theory of Everything, and most of the other people, especially I'm a big fan of Carl Sagan. I think I read every book published by Carl Sagan so far. That gave me a lot of insight about how to be, not only how to be an astronomer, but how to be a scientist on its own,
Mm.
because it gives you a nice information. But that article, when published in 2013, got me really, really excited about this field. You are able to catch a photon that you are not able to see in your eyes, and
Yeah.
with the help of these a few photons, you are able to talk about the invisible matter that is triggering the rotation of galaxies. That idea just stuck in my mind, and I am still, this is my life goal. I still want to go work on the dark matter processes, and that came to the physics department. And the reason why I chose physics, not astronomy, as a department in undergraduate, was that just like I talked in this meeting, I wanted to familiarize myself with the physical concepts first. So
Mm-hmm.
I believe astronomy and astrophysics is a subfield of physics. I am not one of the it's a big deal in Turkey. There are people, discussions are going on. Is astronomy is a different field on itself? Or I believe in order to become a good astronomer, you need to learn about physics as well,
Mm-hmm.
in order to get this pure aspect in the general picture. You will be able to control telescopes, talk about which location of the stars are going on, but you won't be learning about the interior of the star, or how the star is going through an evolution process.
That's a great
So that is
point.
the reason
Yeah.
why yes, that is the reason why I started studying physics, and then I got familiarized myself with astrophysics. I met with some nice professors from my university, which is the reason I stayed in Turkey for masters, actually, because I was spending such a nice time with my group, and we're actually working on an article right now in a very interesting source that is a very giant star next to a neutron star, and that giant star is just like a Kohinoor sneezing, sending series of matter to the infecting the neutron star. So yeah, I can share you with when that one is published. We are looking for some components in the spectrum analysis. The reason why I am studying high energy astronomy right now is actually initially was because it was the most available. Firstly, it doesn't always work in a linear way. You want to work on cosmology, but if there is not any other one accessible to you doing cosmology, that things are getting difficult. I understood that the professor that I really wanted to work with in our university was an expert in binaries. In order to work with him, I was looking for some high energy astrophysics and astronomy papers and NASA publications. By the way, I highly suggest you to do that. There is an enormous resource about NASA's ADS system and the archives of AstroPH. You can just subscribe to AstroPH platform and then get regular emails about astrophysical papers and publications. So that was I was doing actually when I was an undergraduate. I learned about the accretion disks of the black holes, and it fascinated me. There was this source which was my undergraduate thesis with my supervisor. We were able to calculate the rotational speed of the black hole by looking at the spectrum of iron, and that idea fascinated me, and actually that made me change my mind. I'm really curious about the mechanisms of the accretion disks of black holes and neutron stars. This is what I'm doing right now.
Wow, yeah. That was really an amazing overview to your journey about how you became interested into astronomy and how it got changed, in a while. I think everybody who is attending this meeting wants to do something in astronomy, and it is really amazing talking to a young astrophysicist who has been through this journey of age, so everybody can kind of connect. And so otherwise, when we think of astrophysicists or scientists, we think about them as some people in white coat working with some chemicals or in a lab or something like that. But I think connecting with you over here on such a personal level would actually encourage them understanding your journey as well. It makes them seem like it's quite close to them, and that's what kind of boosts everybody. So one last question from my side to you before ending up this meeting is, could you tell me a few specific things that we all will get to learn after finishing your course?
Okay, that's a wonderful question. Thank you. So basically, as I said, there will be 5 different aspects of this course, and each of those things are somewhat related to each other, but they will be giving you the ideas of different parts of this field, for all the way from the theoretical part to the engineering part and to the data analysis and statistics part. So first and foremost, you will be able to after this course, if you this course will give you the power to learn about the concepts that you will hear about the publications and the scientific studies related to those fields. Like if you hear a news about a neutron star, you will be able to understand the physical mechanisms that triggered they shoot out these high energy particles. This is the first thing to gain from this course. The second one is that you will learn, you will be able to understand the classifications made by the astrophysicists in terms of the high energy sources like black holes and neutron stars, because I will be giving you an information that is with the same terminology that is used by the astrophysicists. So you will be able to understand from that perspective. The third one is that you will learn about the general knowledge about X-ray. So you will be fascinated that by the fact that how young this field is, how soon we learned about the powers of X-rays and gamma rays. We are able to how short time we have been able to have this idea actually. So you will have the general knowledge, and you will also know you will also try to grasp the idea about the instrumentation of this place of actually the instruments that they use to capture the photons. So you will be able to get some instrumentational idea as well. You will be able to know the locations where you can download observational data for the high energy astrophysics. the extra astronomy and gamma ray astronomy, and then you will be able to just to see how scientists today, observational astrophysicists, are conducting data analysis process for spectral analysis. You will be able to see that. But as I said in the course, that won't make you a scientist. That won't make you, unfortunately, I wish it was that easy, but that will just give you the general idea. So you will need to work on your own to try to go into expertise about this field. Every single thing that I will tell you here is a field on its own, and people spending their years to establish a function stable ideas of those things. Like there's a theoretical part, there is the astrophysicist part, and then there is the instrumentation and engineering part. There is the statistics part, and then there is the observational analysis part. So it goes on like a ladder, and each you need to do on your own, to your own research, to your own study, related to those 5 things. My courses will guide you to the right direction, the direction that I think is right. I would say.
Yeah, that's perfect. I mean, more than anything else, I'm looking forward to the part where I will get to do my own thing in this particular field from whatever I have learned with your lectures. Even though it's not what the scientists exactly do, but it's like the perfect first step into this, and it gives you like the real pleasure of doing science, and that's what we all are craving over here. I'm very sure about it. Now I wanna really thank you all for taking the time today, and not just today. You have been working on this course since past 3 weeks now, almost a month, and it's going to be hard work until November 29th, I'm sure, and we are all going to take this journey together. And I really just want to thank you from the bottom of my heart that you decided to join AstronEra with this experiment and come on board as our instructor.
I just thank you very much for this opportunity. It's a pleasure to working with my friends again after such a long time, and also there are also some people from Turkey and from our department, from our society as well. Please feel free to contact Shweta as well. I hope that we can do some more collaborations with our society, between our society and AstronEra as well, and this collaboration will continue in the future.
Yes, that's perfect. All right, then let's call it the evening for now, and we'll see you guys soon. Until then, clear skies.
Clear skies.